Welcome back to the Fluid Dynamic Principles series from Pump Design Lab. In this course, we're trying to answer a deep but practical question. How do centrifugal pumps really move fluid? From reference frames and velocity triangles to head efficiency and hydraulic forces. In this episode, we focus on one of the most important foundations, flow in the absolute and relative reference frame. Why this topic matters. Inside every centrifugal pump, there are two main ways to look at the same flow. The casing sees one picture. The impeller sees another. The casing sees the absolute flow. The impeller sees a relative flow. Both viewpoints are valid. Both are necessary. Together, they drive how we draw velocity triangles, how we calculate head, and how we understand hydraulic forces inside the machine. Reference frames. So what is a reference frame? A reference frame is simply a viewpoint from which we observe motion. The same movement can look different depending on where you stand. Velocities are always measured relative to a chosen frame. Imagine a ball moving on a rotating disc. From a stationary view, standing outside, the ball traces a spiral path across the disc. From a view, a ball tossed inside a car. While watching from outside, it follows the wavy pattern motion. But the same ball appears to move in a straight path when watching inside the car. The ball's motion didn't change. Only the observer changed. That change of observer is what we mean when we talk about changing reference frames. Peripheral velocity U. Between these two frames, we have one more important quantity. The peripheral velocity, usually called U, U is the tangential speed of the impeller at a certain radius. If the impeller rotates with angular speed omega and the fluid particle is at radius r, then U equals omega times r. So U tells us how fast the rotating frame itself is moving. It increases with radius. The outer edge of the impeller moves fastest. You can think of U as the speed of the moving observer who rides on the blade. Relative reference frame. Now change your view. Shrink yourself and stand on an impeller blade, rotating with it. From this viewpoint, the casing and the rest of the world seem to be spinning, but you feel stationary on the blade. This is the relative reference frame. Here we talk about relative velocity, usually written as W. Relative velocity, W, describes how the fluid appears to move relative to the blade surface, how the flow enters and leaves the blade passage, and how well the blade angles match the flow, which controls incidence and shock. Blade loading, incidence angle, and the flow inside the channels between blades are all described using this relative velocity W. Absolute reference frame. Let's start with the absolute reference frame. Here we imagine someone standing on the plant floor, looking at the pump from outside, or a CFD model built in a stationary domain. In this frame, we talk about absolute velocity, usually denoted by C. Absolute velocity, C, tells us how the fluid moves relative to the casing, what the inlet and outlet conditions look like, and how the fluid interacts with the piping system. When we draw system curves or think about suction and discharge conditions, we are working in this absolute frame. Core relationship, C equals U plus W. Now we put these three velocities together. There's one core relationship that appears everywhere in turbomachinery. C equals U plus W. This is a vector equation, not just a scalar sum. It says absolute velocity C equals blade or frame speed U plus relative velocity W. In other words, the motion of the fluid as seen from the casing equals the motion of the blade itself plus the motion of the fluid relative to that blade. Because these are vectors, direction matters as much as magnitude. If W points opposite to U, they partially cancel. If W has radial and tangential components, then C will too. This relation is at the heart of velocity triangles. Train analogy. To make this idea concrete, think of a simple train example. Imagine a passenger walking inside a moving train. The train moves at some speed U relative to the ground. The passenger walks at speed W relative to the train carriage. To someone standing on the platform, the passenger's speed relative to ground is C. So here again, C equals U plus W. In a pump, U is the speed of the impeller, W is the speed of the fluid relative to the impeller blades, and C is the speed of the fluid relative to the casing. Velocity triangles. So how do we keep track of these three velocities and their directions? We use velocity triangles. A velocity triangle is a geometric tool that links the absolute velocity c, the blade or peripheral velocity u, and the relative velocity w together with the flow angles alpha and beta. We draw these triangles at the impeller inlet and at the impeller outlet. They're the shared language of pumps in almost every other turbo machine. Fans, compressors, turbines all use velocity triangles. Anatomy of the triangle. Let's look at the basic triangle. First, draw u as a horizontal arrow representing blade speed. From the same starting point, draw w at some angle. This is the relative velocity. The vector that completes the triangle is c, the absolute velocity. We also define two angles. Alpha is the absolute flow angle, the angle between c and the tangential direction. Beta is the relative flow angle, the angle between w and the tangential direction, often matching the blade angle. Inlet triangle. Design condition. Let's move to the inlet triangle and see what happens at the design condition. At the design point, we want the flow to enter the impeller without shock. That means the relative velocity w at the inlet should align with the blade angle. In the triangle, w points exactly along the blade surface. There is no sudden change in direction between the incoming flow and the blade. The flow enters smoothly into blade passage. Losses are reduced and inlet efficiency is high. The inlet triangle defines u, the inlet blade speed, c, the absolute velocity at inlet, w, the relative velocity at inlet, alpha 1, the absolute flow angle, and beta 1, the relative flow angle at the inlet, matching the blade. Outlet triangle, where head is made. Now look again at the outlet triangle. This is where most of the head is generated. In concept, the Euler equation tells us the change in tangential or whirl, part of C from inlet to outlet sets the pump head. So, a larger outlet blade speeds U2, more turning of the flow between inlet and outlet, and a bigger change in the whirl component of C, all contribute to higher head. At the outlet, the triangle defines U2 outlet blade speed, C2 absolute outlet velocity, W2 relative outlet velocity, alpha 2 absolute outlet flow angle, and beta 2 relative outlet flow angle tied to the blade shape. We'll derive the full Euler equation in a later episode, but for now remember the idea. Head comes from how much the pump changes the whirl component of the absolute velocity. Components of C. Absolute velocity, C can be split into two components. A tangential component, often called the whirl component, and a radial component, often called the flow component. In the triangle, if you drop a perpendicular from the tip of C down to the horizontal axis, the horizontal projection is the whirl component, and the vertical projection is the radial component. We can call them Cm or C theta for the whirl component, and Cr for the radial component. This split is very important. The whirl component is what drives head generation in the Euler equation, and the radial component is what sets the volume flow rate through the machine. Euler head depends on the whirl component, not on the full magnitude of C. Reading the triangle means the horizontal side is blade speed U, one slanted side is absolute velocity C, the other slanted side is relative velocity W, and the angles alpha and beta tell us how the flow is oriented in each frame. Whirl and flow. Impeller velocity triangles. Head versus flow. Now, using those components, let's see how the outlet velocity triangles trade head against flow. On the triangle on the left, the absolute outlet velocity C2 is tilted more horizontally. The horizontal part, the whirl component C sub M, is large. The vertical part, the flow component C sub R, is smaller. That means the pump is putting more of the fluid's velocity into whirl. This gives more head, because the Euler head depends on the whirl component. But the radial component is smaller, so we get less volume flow. So the left triangle represents less flow and more head. On the triangle on the right, C2 is tilted more vertically. Here the whirl component C sub M is shorter, and the radial flow component C sub R is larger. Now, more of the velocity goes into the radial flow direction. That gives more flow, because C sub sets how much fluid leave the impeller. But the whirl component is smaller, so the pump produces less head. So the right triangle represents more flow and less head. Notice that in both triangles, the blade speed U2 is the same. It is the way C2 splits into whirl and flow components that changes the balance between head and flow. Riding on the blade. Let's see this from the impeller's point of view. Imagine you ride on the blade. From your perspective, at the inlet, the fluid approaches you with relative velocity W, and at the outlet, it leaves with relative velocity W2. You don't see C or U directly. You only see W. The directions of W and W2 tell you exactly what the inlet blade angle must be and what the outlet blade angle must be. Blade shape is chosen from this relative view. We design the blade so that W and W2 follow the surfaces smoothly, avoiding incidence and separation. Same motion, two pictures. Now connect all this back to reference frames. The same fluid motion can look completely different in the two frames. In the relative frame, attached to the blades, flow seems to run almost straight along the channels between blades. In the absolute frame, attached to the casing, the same fluid appears to trace a spiral path through the rotating impeller. Nothing physical has changed about the fluid. Only your position, your reference frame, changed. This is why it is so important to be clear about which frame each velocity belongs to. Forces in a rotating frame. When we work in a rotating frame, something extra appears in the equations of motion. The effective acceleration includes additional terms, a centrifugal term, and a Coriolis term. We won't derive them here, but you should know they exist. These extra terms influence how pressure is distributed inside the passages, how secondary flows develop, and how forces act inside the rotating impeller. So, working in a relative frame gives deep insight into blade design, but also means carrying these extra acceleration terms. Common pitfalls. Engineers often get into trouble when they forget about frames. Here are some common mistakes. Mixing frames. Reading an inlet angle from absolute velocity when that angle really belongs to the relative velocity W. Getting forces wrong. Estimating hydraulic forces while thinking only in one frame and ignoring the other. And path confusion. Wondering why flow looks radial in one view but spiral in another without realizing the frame has changed. The fix is simple but crucial. Always know which frame each velocity lives in, and always be aware whether you are talking about U, W, or C, CFD, and experiments. These ideas also show up clearly in CFD and experiments. In CFD, the equations are often solved in the absolute frame. The results, absolute velocity C and pressure fields, are then analyzed and sometimes converted into relative quantities to understand how the flow behaves with respect to the blades. In PIV or LDV experiments, instruments usually measure absolute velocities in the flow. To interpret what the flow is doing relative to the blade, those measurements must be converted into the relative frame using the relationship C equals U plus W. So both CFD and lab measurements quietly rely on this understanding of frames and velocities. Key takeaways. Let's recap the essentials. Inside a pump, we always talk about two frames. The casing frame, which is absolute, and the impeller frame, which is relative. We always talk about three velocities. U, the blade speed, W, the relative velocity, and C, the absolute velocity. They are related by C equals U plus W, added as vectors, not just numbers. We use velocity triangles at the inlet and at the outlet to organize all of this in a clear geometric way. And those triangles control how the pump trades head against flow. Where this leads, these ideas are not the end. They are the beginning. They unlock what comes next. The Euler equation, which connects the velocity triangles directly to pump head, part load behavior and incidence. What happens when we move away from the design point and blades no longer see the ideal relative velocity? And secondary flows and hydraulic forces. How the loads on the impeller and bearings emerge from the flow patterns. In the upcoming episodes, we'll bring in conservation laws and connect them with these velocity triangles to build towards pump head and full performance curves. Thank you If this episode helped absolute versus relative flow make sense, then you're ready for the next steps in centrifugal pump design. Subscribe to Pump Design Lab if you haven't already. This series will keep building directly on these ideas and connect them to real design decisions and real machines. Thanks for watching, and see you in the next episode.